So welcome to Herd Inquiries. My name is Mike Panchenko, or Pancakes is what other folks call me. So I won't be able to see my notes, but hopefully I won't forget anything. You can actually, the slides are online already. I'll give the URL at the end. But anyway, now that the computer is working, we can start. So my name is Pancakes, or Mike. I work at Urban Airship on the messaging team, and I came from the, you know what, I am going to mirror these displays because this is not going to work. Oh, I see. I can't even see that over there. There we go. Jeez. There we go. Okay. Sorry about that. Somehow off center. All right. Anyway, I came over to Urban Airship from the Simple Geo storage platform, and the reason Urban Airship acquired the Simple Geo storage platform was very specifically for the end goal of sending push notifications to folks based on where their phone is. It's the marketer's dream. They're obviously sort of the target audience because being able to say, I want to send notifications to people specifically in a location by polygon, and being able to access, even more importantly, being able to send notifications to people based on where they had been recently is incredibly powerful. The thing everybody always talks about is engagement, and if we're to use that term, which we only will for a second, a notification is way more engaging if it has more to do with you. The more it has to do with you, the more likely you are to actually be interested in it. So where you are geographically is an incredibly important aspect of that. And if the user trusts the publisher enough to give them that location, it opens the door to a much more productive, hopefully, suggestion path. Now, when we started thinking about it, it became very clear that just offering location predicates only by themselves isn't very appetizing or attractive, especially when we already order being able to send notifications by tag. Because launching a feature that says, okay, well, you used to be able to query by tags, now you can also query by location, but not at the same time, it's sort of, it's kind of hard to wrap that in a nice product and do anything with it. So it became very clear immediately that we're going to have to do both and at the same time, and in an arbitrarily complex fashion, which means that the predicates would probably be nested and several levels deep. So these things are very nice, but they're pretty difficult. Not very many providers offer anything like that. Certainly not at a large data size. And when I say providers, I mean people that would compete with Urban Airship, not databases. So this is the sort of screenshot of the product from the homepage, right? So you can see that there's a screenshot of the UI where someone picked the San Francisco, like sort of general vicinity to push to, and this is sort of the beginning of it. The sort of possibilities, right, as you start going down that path become pretty staggering. So the requirements from the technical perspective, when this was all hashed out and when we started talking about it, actually building it, were load time to first push. So once someone makes an API request, the pushes should start going out immediately, so that if they have their own devices, if a customer has their own device which most people that use our services have their own devices hooked up so that they can see when the pushes get there. So if you have some sort of a prefetch period or some sort of warm-up or anything like that, they'll notice immediately, and they'll say, well, it took 10 minutes or whatever, however long. Right? So it has to start going out right away. It has to go at a constant high throughput, although we'll see later that there's a caveat to that. And it has to be able to hit millions of devices within seconds. And also, it has to, it had to be horizontally scalable out of the box. So basically, all the things. This is one of my favorite quotes. Perhaps you'd also like the apartment, or the key to the apartment where the money is stashed, and they did. So basically, it was a tall order, and we started trying to plan what to do about it. This is from a Russian book that was made into a Mel Brooks film called 12 Chairs. I highly recommend both the book and the film, although that's from the Russian version of the film, for anyone that's going to call me out on that. Then there's also this other little bit where when you're ready to send the push, there's all this platform-specific and device-specific data that you have to address. So, for example, we have to have a consistent identifier for a device within our system because that's how we know which device we're talking about with its tags, its location, et cetera. But providers often change the token, right? That's why they have the tokens, is in the event of any sort of security or for any number of reasons, the tokens can change. So when we're ready to send the push, we need to go and look up what the token is right now. Otherwise, there's no way we're going to know if we're sending to the right device. Furthermore, we get notified when this token changes. So this data, just to be clear, is stored. We can store it locally. We can own that data or a copy of that data, but we still have to do the lookup. Then there's things like quiet time and badges, which are quiet time is specifying that you don't want to be bothered during a certain time, and some devices will handle that at the device level, at the OS level, but other providers don't. So, but you still want to offer that feature because nothing's more annoying than a push notification at 3 in the morning. So you have to be able to say, okay, well, I'm about to send this push, but did this person specify quiet time? We have to handle that on our end for certain platforms. So that's another thing that's device-specific that has to be looked up. And then badges are, we handle those red little badges for our users, so you can say send a push and also increment the badge, but we maintain that count, and you can increment and decrement it through the API so that you don't have to run a service to deal with that. So this is critical because a naive implementation of this ends up in a key value lookup right before every push, just random I/O for every single device that the push is going out to, but your working set is all the devices. So you have to be a little careful with what happens there. So this sort of emerged as we went into development, and it was a big problem. So a quick overview of what we're dealing with. Tag predicates were something that existed in our SDK. Man, slides are getting cut off. Well, that's life. So what that says is tags set via the device SDK or directly by the developer, only the is cut off, through the API. And the most likely use is expressing some preference. Whether it's a band you like, a sports team you like, or another important one is what kind of notifications you want to receive. A lot of applications, particularly sports apps, which turns out love push notifications, will have this whole, here's an example, this whole list of preferences, right, for what kind of notifications you want to receive. So not only could you be following multiple teams, you could also have specific preferences for when you want to be notified. You might not care about when the game starts. You might already know. And if you only offer disjunctive operators, which is or, users end up doing things like creating the matrix of all the different possibilities, and based on your preferences, setting that one tag. Now that matrix grows very quickly, and I mean, you end up with a mess. We don't want that in our indexes. That bloats the indexes. And it's just not a very nice way of dealing with it. So very quickly, we realized that as part of this project, we'd also have to start supporting complex predicates for tags, including conjunctive and conjunctive operators and negation. So location predicates were sort of a new concept to the push service. Didn't really exist, so we sort of had to do a lot of customer discovery and stuff like that and figure out what people actually wanted. And what we landed on were two kinds of queries. One was last seen in a specific polygon, which is sort of the obvious one, like send a push to everyone that whose last location is in Baltimore. Hello, welcome to Surge. Or anyone that has been in a polygon within an interval. And first, I was having a lot of trouble wrapping my mind around why necessarily people would want to do that. But there's very obvious things like identifying people that had been to an event after the fact. Like if you want to send a push notification to someone that you know went to the opera one night, for example. So you can say, OK, anyone that's been to the opera house and has this app installed within the last 3 hours, that they had to have been there for the show, ask them what they thought about the show or send them some bonus material or something like that. Well, and then over the long term, you end up sort of having some longer run targeting you can do as well. So recall, we came from Simple Geo, and here's a slide from a 2010 presentation of Mike Malone talking about the Simple Geo storage index, and Mike was the sort of mastermind behind the spatial tech at Urban Airship, and he was the other person on a team of 2.5 that worked on this for about 2 years. So we built up a pretty awesome index. I'm not going to go too deep into what the index does because that's beyond the scope of this talk, but the important thing is to know is basically that the spatial predicates that we identified could be satisfied fairly easily by the index that we had for spatial queries. Primarily by the KD tree, which is a spatial data structure that I could spend like 3 hours talking about, and then everyone would be mad because that's not what they're here for. The point is, we had to reconcile this data store that was really good at location queries, but couldn't really be made to fit easily tag queries. And the important property of tag queries that made this not work, no, too soon for that guy. Maybe it's never too soon for that guy. But basically, we couldn't figure out how to make an arbitrary number of tags fit into that index because it was a little bit rigid. It was something we built for ourselves for our specific use case. So the code just wasn't there to say, okay, and someone can assign an arbitrary number of arbitrary attributes because tags are schemaless. You can't really make developers tell you what their tags are going to be in advance because that sets up a whole separate headache of how do you update that, how do you even represent that. So basically, that index wasn't fit for it, so we had to come up with some other system for tags. Now, you might say, well, why don't you just put some tables into a relational database management system? And this guy, if he checks where his links are coming from, is never going to set photos to Creative Commons license ever again, because that's just some random guy that I think looks hilarious. He's just really excited about something. Let's pretend it's a database. It's almost certainly a database. But that's definitely something we considered. But I think this is an audience where I think it's pretty easy for me to get away with saying like that just doesn't work at a certain size. I think that's sort of commonly accepted at this point, and I don't have to defend it too much. But we did go down that road. But we already, before we started this project, were dealing with something like this, where there's your RDBMS, there's your data, and there's ops just holding the door shut so that it doesn't explode. When you get to a certain size of data, so we're dealing with hundreds of millions, trending towards 1 billion of installs of apps that are using our SDK. That's devices that are sending us data and devices that we have to be able to push to. That's a hell of a Postgres instance. That's a hell of a backup process. That's a hell of a failover. That's a hell of a sharding scheme once you start sharding. Most of our customers are probably, I didn't didn't go dig up the exact numbers, but pretty confident that most of them are like under 10 million. But then there's like a few really notable exceptions where it's like 100. And then now you have to shard within the app and basically no thanks. So we had to come up with something that wasn't that. And we were all a little spoiled. We had all been working on Cassandra and distributed spatial index on Cassandra. So, it wasn't really appetizing to try to go down that road again. I came from Flickr, where we did go down that road again, or that was the only road at the time. And it worked fine, but certain things you don't start over with. So the net situation is that we could come up with any number of tag solutions. That's a pretty straightforward database problem. It's an index. You have your application, you have your tag, and you have your app ID, and you have, or a device ID, and you have basically a one-to-many relationship. You can store that in HBase, you can store that in a row in Cassandra, you can use the Cassandra ordered partitioner, any number of things will work to some degree, to an acceptable degree. The spatial solution can fit tags, and don't forget about that platform-specific data, which every time you're like, oh, okay, we figured it out, it's like, oh shit, but then there's the platform-specific data. What do we do about that at the end? So we have all these pieces that we can figure out how to solve individually, but not together. But as people are saying a lot recently, it's sort of making a comeback, it's just a matter of code. So then you start thinking, what would the database do? Were we to put this into a relational database, what would it look like? Because probably there's certain pieces of that you can take and borrow. We cheated because we did take and borrow some of that stuff in previous work, so we kind of started going down this avenue of, okay, well, if we were to put this into a database, we'd have 3 tables, maybe 4 if the historical data was in a separate table. There would be the location tables, the tag tables, and the platform-specific data, and there would just be a mess of joins everywhere. The tag data, due to the fact that it's high cardinality and arbitrary, would probably be self-joining, and I don't know how many people have done like hardcore self-joining, where you have like, start to get into the 10s and the 100s. It's, your disks just don't go, I mean, maybe you have SSDs, but you know, they just don't go in that many directions at the same time. So, and then the platform-specific data has to basically be joined to the end of it all. And then there's also inline operations like counter increments for badges that have to happen. But this is all something you could probably do with like a crazy stored procedure in Postgres. So the tables would probably look roughly like that. But the important takeaway here is that the primary key for everything is the app ID and the device ID. And now there's a little aside, and this slide doesn't really fit anywhere in the presentation without interrupting whatever I'm talking about. So there it is. Who's familiar with data clustering, like index clustering? 1, 2, 3, good. 4, yes. Lead architect of Urban Airship knows about clustering. So this isn't like node clustering. This is when you write an index in Postgres, you can run a command that says cluster and give it the name of the index. And what that does is takes all the rows on disk and rearranges them in the order that that index is. So then when you're querying that index, when you have to read rows off the disk, you're reading them sequentially for the order that index is in. Now MySQL and InnoDB will do this automatically on primary keys. So whatever you set your primary key to, for example, a monotonically increasing numeric ID, rows that sort next to each other by primary key will sort next to each other on disk. So if you have a very common query pattern, for example, if you're always querying things in order of their numeric IDs and you want them in batches, that's a huge optimization because now you're reading things in big swaths off disk. And even on SSDs, that's there's a performance improves by a factor, something like 5 or 10. So on spinny disks, it's orders of magnitude, right? If you can avoid doing random seeks, you're going to be in much better shape. So this is very important for where we go next. Or not next, because it's not quite right next, but I couldn't really figure out where to stick that slide. Keep that in mind, anyway. So then you have the life of a query, right? When you make a query to the database, what happens? The query gets parsed. You're probably involving all 3 or 4 of your tables because you're joining them all together. So the computer turns your SQL query, pretty as it is, with all the subclauses properly indented. It turns into something you can actually read, which is, or understand, which is an abstract tree. That abstract tree is a logical representation of the data you're after, right? It basically represents an iterator over the rows that you want to pull out of the database. However, there's probably multiple ways it can manifest that. So when you run explain, does Postgres have explain? Okay, yeah. So on an RDBMS, when you run explain, it prints out this thing that then you have to go read a book about to understand what's going on. But what that is the query plan, right? So now we flip the table. Now the computer is giving you something it can understand, and you're just like, that looks nothing like what I want. But the point is, it achieves the same data in some way, in a way that it thinks is optimal, right? It maintains statistics about your indexes, about their sizes, their cardinality, and previous queries, and tries to guess what's going to be the cheapest way to get at the data you want. Now, one advancement that happened, and I haven't been following that world too closely, but when, God, now I forget, Drizzle, the sort of fork and rewrite of MySQL, and I don't know, maybe Postgres. Usually when you discover these things, like, oh, someone rewrote MySQL and they did this awesome thing, Postgres had already been doing it for like 10 years and you're embarrassed. But Drizzle started doing this thing where you could run a query, get back the execution plan, and the next time you got to just send back the binary representation of the execution plan. So you could skip the parse phase. That's something we can borrow, and we will in a second. Sorry, the plan phase, a little digression there. The plan phase is to figure out the cheapest way. It comes up with some way it's going to get all this data, and then the perform step is pretty obvious. So there's going to be certain parts of that tree. I'll just skip to the tree. certain parts of this tree, and that long green arrow, don't worry about that long green arrow. That doesn't belong there. The pink arrows point to things that are actually fetching data. The green arrows are pointing to things that are performing some logical operation on it, some sort of relational algebra or Boolean algebra, right? So all this is a join. There's 3 tables. They all have column X, and wherever column X is equal, we want to return that. We want to return those rows. So that's the perform phase, and then it just sends the results back. That's basically it. I obviously simplified this a lot. There's somebody in the crowd is like a hardcore database nerd. Yes, there's there's a lot more, but we're not gonna get too much farther into it because we don't need to for our purposes. So one important thing to note is that those green arrows, those operators only care about tuples of data. As long as they're getting rows from both children that they have, or however many children they have if they support more than one, and those rows have the right column, and they can compare that column, that's all they care about. Logically speaking, abstractly speaking. Obviously, in your RDBMS implementation, they care about very specific tuples. But here's a diagram of a sort merge join. And what we're looking at is you have the disk over here, of course. That's what disks look like. And on the disk, you have 2 relations, S and R. And when you merge them, it effectively reads them in batches off the disk, puts them in a priority queue, and then the whole point is they're both in the same order. You want that same order on the way out, so you look at the first entry on one side and the first entry on the other side, and if they match, that gets added to the result set. If, for example, the right side is at A and the left side is at D, the right side is forwarded until either you hit D, and that's your next result, or you skip D, and then you have to forward the side that had D in the first place, and so you go on until you run out of results. So it's a pretty straightforward algorithm, actually. There is some detail, when you're talking about scanning the entire data set, there's some tricks you have to do to manage it in memory, but that's basically what's happening. Right, so you fetch, you sort, you merge, and you return the matches. Now recall that aside about clustered keys. If your rows are already in index order, you don't have to do that anymore. And all that stuff I just waved my hand past about managing stuff in memory, you don't have to do because you know that the results are coming back in order. You don't have to check whether or not there's results further down that are out of order. You know, you can grant that. Very important optimization. And now we get to the point of what are we actually trying to build here. So that's a large, complicated ecosystem of code, of crazy mathematical theory that I don't know. And if you phrase it like this, query arbitrary combination of spatial and tag data in real time, it sounds like you have to implement all that and spend the next 2 years of your life doing that and then probably write a paper and retire. But the reality is what we really want is to send to devices matching an arbitrary nested predicate. That part still sounds bad. That still sounds hard. But in any order. So what that means is that the ordering in which you execute this doesn't matter. To the end user, they don't care, right? Once whoever is using our API sends their push, they don't care if I get it first and Eric gets it second. As long as we all get it in a certain order, in a certain reasonable amount of time, that's all they care about. So that means we can pick the order, and if you can pick the order, you get basically that clustering optimization. Because if you enforce a global ordering across all of your data stores and all of your queries, you do away with a huge amount of A, just pure I/O and CPU work, and B, complexity. So what you end up with is the location index can return results in ID order. It always could. It can sort on any column. And the trick there is it's actually not clustered on disk. The actual items aren't. But it's an index, and it's a bucketed index. And we can compare the buckets. So the buckets are fetched off of, are read off of disk in the right order. So you're only having to sort within those buckets. So you're only ever having to have one bucket worth of results in memory. So we could easily add clustering because it's underneath. It's just Cassandra, and Cassandra has the notion of a comparator, which is how it determines, like stock Cassandra just writing columns, how it determines what order it writes columns to disk. Now, items in our index, at the end of the day, just end up being columns in Cassandra, and it's trivial to implement an additional comparator in Cassandra that writes it in order of whatever attribute you want it to be in our index layer on top of it. We haven't done that, but we could. But regardless, the other sets of data, it doesn't matter because we can, like I said, we fetch the buckets in the right order, so it ends up not being that big a deal. The tag index is trivial to store in order. Any ordered partitioner like HBase or the Cassandra ordered partitioner will do. Anything that can act like Bigtable basically will work. And same thing for the platform data. So enforcing the global ordering at the storage level is easy. We can do this. This achieves sequential reads for all of our queries, like I discussed earlier, and it's a huge performance win. This is something important. Then, as we were talking about this, we realized one other very important thing. All of the indexes we have, the context here was that we started talking about the query optimization problem. One of the biggest problems is if you have multiple tables you're joining, and say 2 of them have very low cardinality, and 1 of them has very high cardinality, the one that's got a lot more results is going to have to do a lot more skipping. And in a traditional system where you have to do the ordering, you have to do all of that work to iterate through that whole data set. So if you get result 1 on one side and it's 5, and the other side says 500,000, the side that says 5 has to now work through basically 500,000 results just to get up and see if it has a 500,000. And then it does, and it says, OK, next result. And then this side says 500,001, and this side says 2 million. And now you're doing this over and over and over again, right? So it's a lot of work. But there's a but. All of the indexes we just discussed, because they're all ordered partitioners, or can support ordering at the index level, you can do cursor pagination very efficiently. You can skip forward. Instead of doing that process where you're churning on through all the results, you can just say, oh, I need to go to 500,000, and just not even do any of the reads. Both HBase and Cassandra offer facilities, indexes, that I think you can actually tune to be more and more and more aggressive, where it will maintain a sort of sparse skip list of keys, basically. So you can say, OK, well, whereabouts is 500,000, and get really close without actually doing a disk read. You just seek straight there, instead of having to do checkpoints. So again, when you're joining sets of disparate sizes, this is very important. You're basically, you don't have to optimize it that much further. Like that already gets you a long way there. The other important part about all this is that each individual subset only returns the results that the exact set of devices that you're after. There's no post filtering. You're basically hitting an index every time. So now when we look at this picture, first of all, we can cross out the priority queue because we don't need it. We know the order. And second of all, going back to what I said earlier, any logical equivalent to something that produces tuples will do. So take 2 of this diagram, which I drew very professionally. Looks very similar, but instead of the disk, you have 2 databases. You have the query execution engine called GUI Buttercake. You're welcome, Internet. And all that does is buffer the result sets and performs the join. And I'm representing just a simple merge join, but it's I think fairly easy to see how that would scale, because remember earlier we looked at that tree. You can nest those trees any way you want, and if each one of those trees just ends up being that, they can behave as an input to another root node. So basically, we cap the depth of the tree just to prevent too many queries from running at the same time. But if someone really rich wanted to run like a 20 deep complex, effectively join, we just have to get them to pay for the hardware, and then we could do it. So yeah, that's the system we built. How am I doing on time? Because I can't see anything on my screen. Got about a half hour. OK. So that's I actually the amount of protest I got. I want to take time to educate. GUI Buttercake is a legitimate dessert. It's not some disgusting thing I thought of that like you look up on Urban Dictionary. That is something they make in St. Louis, and it's delicious. The amount of people that were disgusted with me for no reason, they dreamt up what it could be at work. They're like, oh, you can't call it that. Jesus, man. Anyway, there it is. It's a little gooey, kind of looks a little runny, but it's delicious. So when we look at what we had actually done, back to what you're here for, all of a sudden this doesn't look so bad, right? It's actually all quite simple when you throw away all the stuff you don't need. You perform you first of all don't have to parse, because you can pass the tree directly in, because we already know what the equivalent is going to be, and the equivalent is going to be the exact thing you asked for. There's no optimization going on. We already have all, like, the indexes are only set up to do one thing and one thing only really, really well, which is also nice from the service-oriented architecture perspective. Like, every query should take about the same amount of time because it's always 1,000 items and it's always hitting the same index. So the individual subqueries are, a dream to monitor because if any of them take longer than they should, like, you immediately know that you have to go debug something. And because there's only ever one equivalent that we're going to perform, as any good NoSQL data store would, we make you build the query yourself. And you're like, come on, man, really? We're going to have to nest JSON now? And it sucks, I know, but it's still better than SQL. Internally, the JSON that you pass into our API gets flipped very casually to, it's a very simple structure, so it's very easy to flip it to a nested protobuf, which is what all of our services speak to each other internally. So basically, GUI Buttercake gets a tree structure, turns it into a set of iterators, and I forgot to include the code in the slides, but the interface for that the whole system is built around it extends iterator, so it has next, and remove, which throws an exception because that shouldn't be there. And then it extends it with two methods, which is skip to, which is what we talked about, where you could skip past a set of results, and inverse, which is used for negating a predicate. And that's it. And I forgot to do a line count, but it's probably like 2,000 lines of code at most. So it turns out that there's a pretty straightforward solution to what we're trying to do. Once it's phrased in in what we want, and right. So the JSON part sucks, but look at the UI you can build around that. I mean, maybe the first time you look at it, it's confusing, but it just makes sense, right? And you can see exactly how that gets turned into a predicate tree. I don't know. Does that make sense to everyone? Does everyone know what's happening here? What are we looking for? We're looking for all the urban airship employees in San Francisco or Portland, because the tag cool people obviously will be applied to anyone that works at urban airship. So that's that. So everybody follow that? Someone nodded. Fantastic. So now what we're all here for, the story time. Interesting things we learned while building this and other similar systems. When you send a push, it turns out people get it. And if it's good, and you're doing a good job of sending useful pushes, they'll click and open it, which opens your app. And a lot of times your app opens a web fragment or makes an API request. And if we send pushes really, really fast, that all happens at the same time, and then your site goes down. Which I find awesome, because that's a hidden interaction if I ever saw one, and I love hidden interactions. Like, someone called and said, you took our site down. And we said, no, we didn't. Come on, man. You just sent a push. It's right there. Everything's fine. But yeah, we now have to build rate limiting into everything, because we are that good. It is that fast that it'll DOS you. But that was an incredibly entertaining ticket to come across. De Morgan's Law is your friend. Who knows De Morgan's Law? Everybody better raise their hands. All right. Well, worried about you. When you forget that your system is supposed to support knots until the day before someone's going to play with it, the launch partner is going to go look at it, you have a long night. And when you have a long night of coding, you end up posting comments like this. Everybody just go ahead and read that. Can everybody read that? I'll read it out loud. I posted this. I'll investigate the implementation. Might not have gotten the logic quite right for buckets. It's possible that what's actually being queried has been places other than Dominican Republic in the last month, which would obviously be incorrect. What I'm really saying is, oh, the logic's wrong. I got to go fix this. So when someone wants the opposite of has been to the Dominican Republic in the last month, what they're after is people that haven't been there, not has been to any other place than the Dominican Republic any other time than last month. So the historical queries are implemented as range queries over a set of buckets, effectively. And an equality constraint on the ID of the place you're after. If you just flip that, you get what this slide says, which is people in marketing and product are playing with it, and they're like, oh, I sent this push, and it seems to have gone to everyone. And you're like, whoa, I got it. I haven't been to the, I don't know. I'll look at it. Yeah, and then you find, and yeah, it's good to, I'd say, generally it helps to understand the logic. Wise words from me several days ago. So yeah, then I have to put this into my slides because I can never actually make that face again, but it describes how I feel about these things so perfectly. When I see those bug reports, it's just like, come on, man. When you figure out what you had done. Here's another one. Attention to detail is important. This was like 3 to 5 hours of debugging that led to a 1-character patch where I literally did not actually invert in the invert function. Penelope is our spatial index. Well, actually, so this is a good code sample. So, driving the camera got crazy, moving around. Skippable Iterator is that base interface that I talked about. It's just an iterator that can skip. Everything in the system, the iterator is parameterized so that I can test it more easily, but the system uses lists of strings, which are tuples of results, and all of these things are implementations of it. The beautiful part about this guy is that anything that queries a database for its results, there's a base class called buffering skippable iterator, which just fetches results 1,000 at a time and puts them in a buffer. And the implementation of the spatial index iterator is basically 5 lines of code that says, fetch 1,000 results after this cursor and return them. So when you add a new data source, you make a new one of these that fetches 1,000 lines after this cursor and returns it. So that's just something I'm really proud of because it ended up being a very simple system to extend. And what you get with that is that for testing, you make a base class that enforces the contract, and all you need to provide it is an instance of your iterator that is backed by the appropriate set of data. And then you get basically a free test suite for every new database you add, and all you have to do is index the data set that it's expecting for the tests. So things like that are nice when you're suddenly adding iterators at 2 a.m. because you forgot about knots. Anyway, here's my favorite part of this talk, where I tell you about how much of an idiot I am. So because of an accident of history, nope, too soon. Because of an accident of history, the way we implemented cursor pagination was greater than or equals instead of greater than. So that's basically the 2 ways you can implement cursor. Either you say, OK, the next page should start with this result, which is skip 2, or the next page should be after this result, should start after this result, which is skip past. So when we implemented the spatial index, we kind of newspapered over some dirt and didn't really parse the ranges being passed in, and just assumed that it was closed at the beginning and opened at the end, because that's how all the ranges inside the tree structures in the database worked, and it was just so natural for us at the time to be like, oh, of course, we'll just assume that, because you can work around that anyway. Nobody seemed to complain. And when we started building this, that was still the case. So because that was one of the target systems for the execution engine, we made everything do that. Problem with this is that sometimes when you're tracking people's historical location, certain queries will return 1,001 of the same ID. And then you say, OK, I have a next page because there's 1,001 results. So that means my next page will skip to the 1,001st result, which brings you to the same page. And that's just a tight loop. And you draw this. This is a queue on one of our delivery servers, because there went my little single instance of GUI Buttercake just going nuts over that one ID. Here's the graph for pushes for the test app. It's the end of the day. This is in UTC. Everyone went home. And about 8 p.m., I think, or somewhere at 7 or 8 p.m., I get a text from this guy Ben, that is another Simple Geo guy, and he goes, yo, dog, I just got like a million pushes. My phone overheated and turned off in my pocket. And the reason he had IM'd me is because during testing, what I would do is I would literally just run a tight loop, sending pushes, like actually sending individual pushes to like everyone in the company, and everybody loved it because their phones would just go wild. So he immediately thought that I was just messing with him. And of course, it was like 7 or 8 p.m., and I said, shit, because I hadn't done anything like that. And the only other thing that could have happened is someone playing with the UI as they were testing it, as it was getting for release, sent a push, and that happened. So you're going to have a bad time if you do this. Also, it turned Eric into Lumberg. Eric IM'd me and said, hey, what's going on with that ticket? And I couldn't blame him, because then Eric's boss also IM'd me, having already IM'd him, and said, hey, because what's happening in their mind is the Olympic Organizing Committee is going to get this 2 days from now and send a push and get like 1 million of them, and then we're not going to do this anymore. So the solution is implement uniques at the data stores, which is a nice feature to have anyway, and we're glad we did it. Use exclusive pagination, which is a trivial patch, right? Probably part of the reason we didn't do it in the first place is because we said, well, we don't want to do like advanced parsing, and like it ended up being a regex, and that's all it should have ever been, because when at the point that we parse it, we get just the range. So it's pretty trivial to say, okay, what bracket is this? What bracket is this? And then my system should have, from the get-go, enforced monotonic order, because that's what the whole damn thing is built on, right? That assumption that everything is in ID order. Why would anything ever be anything other than ID order? And don't be an idiot. That's the most important takeaway. If you learn anything from me here at Surge today, it's don't be an idiot. Speaking a little more to the operational side of things, the part that sucks is that everything is an integration point for the system. And it got a little better because we put another step in the middle, but when we were initially developing it, it was talking to all the databases and talking to all the different delivery services for all the different platforms. So if anybody went to my talk last year, I talked a lot about how you don't want very many integration points anywhere, and now I was the guy maintaining that system. But there's an upside. It's really easy to track down failures, because you just look at the graphs for GUI Buttercake, and whichever database is slow is the database. And you can basically start paging on just GUI Buttercake metrics. The downside is that then anytime anything is wrong, you're paging. So it's a double-edged sword, so to speak. That's actually it. I don't have any more slides. So if anybody has questions, I think we have a few minutes left. 18 minutes for questions. I went a little fast. All right. Does anybody have questions? No, it's not at all the same index. No. Well, so it's the same ordering. Global ordering is very different from the same index. So since I have 18 minutes, let's talk about the simple geospatial store. So that's actually a very different beast than anything else, right? So the tag index is probably going into, what are we, Eric, it's in Cassandra, right? The tag stuff? Yeah, it's just going into Cassandra, and it's straight up, your key is your application, your tag, and your device. And when you want all the devices for a tag, you scan those. Right. But when you're doing a spatial query, like, have you indexed spatial data for? Yeah, okay. So that looks very different. That usually looks like a KD tree or an R tree, which is a multi-dimensional tree where in one dimension, let's say, would be latitude, and one dimension would be longitude. And as you put data into it, actually, let me go back to that slide, because I picked the perfect slide to stick in here from that presentation, because I can actually use that. Let's look at this guy again. Everybody feel good. Okay. So the idea, I know this is just a lot of square rectangles and circles here, but the idea is this is the world, flattened out. You put a point in here. The reason there's a line is because the whole world represents the root node of your index. And these two guys represent the two split panes. As you add more and more data to here, you start splitting further. So if you have all your data is here, you start splitting this guy down into smaller and smaller pieces. And they're represented by buckets in the index. And in our case, the big thing we did is that the tree is overlaid on Cassandra. Individual buckets in the tree are keys in Cassandra. So as your tree grows, it just gets spread out evenly over Cassandra. And as it gets bigger and bigger and you need more space, you just grow your Cassandra cluster the same way you would if you were using it for a traditional Cassandra use case, and life's friggin' groovy. Very different than, right, so it's not the same index at all. It's, so that's what I was getting at. When you query this, you've got the individual keys that contain all your features. The individual keys also contain summary information about what's in them, like what is the bounding box. Like in the simplest case, it's what is the bounding box that is contained by this particular bucket in the index. You can order those. And if one of the dimensions in your tree is ID, and you're splitting on IDs, your buckets will say, OK, I have IDs A through C. The next bucket has IDs C through F, et cetera, et cetera. So when you're fetching things off disk, as you're doing your query, let's say you're doing a polygon query, the first thing you're going to say is, does this bucket intersect this polygon? If it does, there's probably some result in there that I want. And then you're going to put it in a priority queue with other buckets. So you get the ordering there already, because the priority queue is ordered by ID. You know what IDs that bucket contains, right? So you can order the buckets, and then you only need to order the results within the individual buckets, because the global ordering will already be enforced by the ordering of the buckets.
So the buckets are ordered
by the same thing.
By the app ID and
yeah.
tag ID, but you have another index that orders them in a tree structure by geolocation.
Well, that's the query you're performing, yeah. The traversal you're performing constrains all the buckets you're evaluating satisfy the constraint. But you also evaluate them in the order of your sort, right? So
essentially there's two kinds of indexes going in parallel.
That's why this is, to me, that's why this whole thing is interesting, right? Is that you have completely different indexes in completely different systems that you're able to effectively run joins against for our purposes. Now, when I talked about earlier about all the work we didn't have to do because of our specific use case, that doesn't mean we can't do it later. All that stuff that I crossed out on the query parsing side, you could add back in there if you have the time and the business need, which we currently don't, but we might one day. And then the possibilities start blowing your mind, because now, I mean, you could do a lot with that. To speak to your point further, if we had like a year's time to experiment with things, we could probably figure out a way to put the tag index in the same data store and just do the merge join inside that data store. But that was considered, I mean, by me, among other people, a high-risk investment, because that was a completely different use case than what it was built for.
So what are the data stores then? You got the
Cassandra for tags, and I think Cassandra for the. Oh, I forgot to talk about that. We forgot to get back to the platform-specific data, so I'll actually swing right back into that because it applies. Cassandra for tags, Cassandra for the platform-specific stuff, and the spatial index for location data. So one important note is that when you do the global ordering, that location data, that platform-specific data that I kept talking about needing to be merged in at the end, ends up in that same order. So when you're done, you take your fully filtered set, right? You've got your set of devices that satisfy your query. You run it through a system that can talk to the fully ordered list of platform-specific data, and you end up basically doing the same thing where you fetch 1,000 at a time from here, scan them, and then in the case of a high cardinality query where a lot of the devices out of the total install base satisfy it, you just get a very efficient operation because you're just scanning through that linearly, which you'd have to do anyway, right? And in the case of a sparse query, where you only got, let's say, 5 out of 5 million devices, because it's an ordered partitioner, you can skip around and say, OK, I need 5, I need 5 million, and not do any of the reads in between, right? And depending on how optimized your indexes are, that's something you can tune and make better. If you have more memory, you can make your index better within that. And somewhere in the middle, there's the degenerate use case where you have to skip a lot more but it's still better than just doing random I/O around a cluster. So, did that answer your question?
Geospatial index is stored on what actual database technology?
Something simple geo built. Yeah. There's actually, if you search cloud stock simple geo 2010, that's the talk that gets passed around commonly if you're interested in that. Yeah, sorry. Yeah, I thought I would run out of time, and then I didn't. It takes a lot longer when you're not nervous and talking fast. Any other questions?
Are you across data centers? Or, what does the WAN link look like? How many nodes do you have? That sort of thing.
Eric, would you like to speak to that? Because I have no idea.
It's a single facility right now. We're migrating to multi-facility, and each of the backing pieces that Panchenko was talking about is actually popped up by a different cluster. They're independent clusters. We don't match everything in one. We move them in different sequences, upgrade them in different cadences, etc. So to answer that more precisely, that might as well.
The rings are relatively small by larger scale Cassandra clusters, so they're about 10 each with stock standard rotational media on them. We're definitely migrating more towards SSDs for the Cassandra clusters.
Did everybody hear that? Should I repeat that? No? Yes? All right. Looks like the people that wanted got it. Anybody else? Going once, going twice. All right. Thank you. And if you thought any of what I talked about was cool or just generally want a job, we're hiring. There's a ton of jobs available. The references are at the end of the slides for the database papers. They're an awesome read if you're interested in that kind of stuff. And these slides will be online. I'll probably put the link on Twitter because it's still too long to spell out. Okay, thank you.